All right, so what was the first function we're supposed to write? All right, so mux, which takes an array of input names as a parameter and displays an accurate truth table for the mux as we see in 5.2.1. Note that the size of the array will dictate the number of selector bits needed. All right, so let's look at 5.2.1. So here's 5.2, we look at, and here's 5.2.1. So this is a 4x1 multiplexer where you have 4 inputs. These are the names of your inputs coming in, right? So I0, I1, I2, I3. And I said in this thing that you were taking in an array of names, right? An array of input names as a parameter. So we can choose to have our input names be the same as what we just saw. All right. And then we should have a number of switches relative, because I mentioned in there that note that the number of switches. So this displays an accurate truth table for the mux as we see in 5.2.1. Know that the size of the array will dictate the number of selector bits needed. What does that mean when I say the size of the array dictates the number of selector bits? Where these guys are the selector bits down here. Why does the size of this dictate the number of these? Possible permutations. Okay, so in this case, I have 4 input bits. What if I had 5? If I had 5, can I represent 5 unique states with 2 bits?
No.
I can only represent 4 unique states with 2 bits. All right, so I need to find the closest power of 2 that is not less than the number of elements in my array. So in this case, my array has 4 elements in it, right? I want to find the largest power of 2, or the smallest power of 2, that can accommodate that many things. If I had 5 things here, I find that 2 to the second power is 4. Can 4 accommodate 5? It can't. 2 to the third power is 8. Can 8 accommodate 5? It can. All right, so we could take in 5 bits here. But we could also take in up to 8 and have the same number of selectors. So the first thing we need to do is we need to have a function that will figure out how many selectors we'll need given a number of inputs. Okay, so let's go into our code here. And we'll just create a new project. All right, this guy will be a Java project. We'll call it, I don't know, memory and stuff. Good enough? All right, so here's memory and stuff. I see you. So just sit back there being all creepy. All right, so this is memory and stuff. And we're going to go ahead and we're going to create our driver in this. It is a programming class. Well, it's a architecture class where we're doing some programming. Well, you can sit in here, just make sure you shut up.
Oh boy.
So driver dot, well, we'll name this guy driver. All right, so.
Can you make it like one bigger?
Who?
Can you make it like one bigger size?
Is that good?
Yeah.
Shut up!
I'm there.
All right, so we'll go ahead and do our public static void main string array args. And we'll make sure that this guy works as a starting project. And it does. Okay. So now we're going to go ahead and we're going to create a, we can actually create our functions in here because we just have 4 methods, right? Now we're writing. So let's see. Well, we have a class called memory,
Brought my gloves.
function called
There you
mux.
go. I'm gonna sit right next to the door.
All right, so we're going to go ahead and I'm just going to write a couple static methods in here. So we're going to say static int. Let's see, why don't we call this guy find num selectors given int num inputs. All right, so find num selectors given num inputs. What does this guy do? It returns for me the power of 2. So the 2 to the what power for number of bits that will accommodate this many unique inputs, right? So if I say 1 bit, one selector only lets me do 2 inputs. 2 selectors lets me do 4 inputs. So I want something that is either greater than or equal to the value that's here. That means it can accommodate it, right? So we're going to say int I is equal to 1. We'll say while math.pow 2 to the ith power, while that guy is less than num inputs I plus plus, return I. So this should get us our number of selectors. So if I want to test that here, I can say system.out.println driver.numSelectors, and if I pass it a 4, this guy should give me a 2. There's my 2. If I pass it a 5, now all of a sudden I've bumped to 3 selectors. There's my 3. If I pass it an 8, I'm still at 3 selectors. If I pass it a 9, I'm now at 4 selectors. Make sense? All right, so I have a nice function that will allow me to keep track of the number of selectors I'm going to need for emulating my multiplexer. Okay, so go back in here. What's the next part? Takes an array of inputs and displays an accurate truth table for that guy. Okie dokie. So we're mimicking the truth table found in 5.2.1. So given 2 selectors, we can represent our various outputs. So 0, 0 translates to our first, well, and this depends on which direction you go with your thing here, but we have to have a unique code for each of these guys. So we can say 0, 0 is representing this guy, 0, 1 is representing this, 1, 0 representing this, 1, 1 representing the next guy, so on and so forth. Okay, so this is a 0, this is a 1, this is a 2, this is a 3, right? So we can convert this if we want to. I mean, you can sit there and mess around with the binary if you want. Or you can just count from 0 to 2 to the number of selector minus 1 power. And those are our unique number of outputs. So let me show you what that guy kind of looks like. So let's have another thing. Static string. Well, that's just going to output this, right? So let's say static void mux. That's going to take in a string array called input names. And then we're going to say int num selectors is equal to driver dot find num selectors given input names dot length. All right, so that'll be my number of selectors. All right, so now I need to count between 0 and 2 to the num selectors minus 1. Those are the things that'll be in my truth table. All right, so let me kind of show you what I mean by that. So I'm going to say int smallest is going to be 0. Int largest is going to be math.pow 2 to the num selectors minus 1. And we're going to say that this guy is an int because it comes back as a double. Math.pow produces a double. So this is 2 to the num selector's power minus 1. So if num selector was a 3, 2 to the third power is an 8. My legal things are 0 to 7. Okay, so we want to make sure that it prints out the right stuff here. So we'll say system.out.println smallest, concatenated with a space, concatenated with largest. All right, and we'll go ahead and we'll give ourselves our input. So we're going to say string input names is equal to what do they call them in here? I0 through I3. I0, I1, I2, I3. Like that. Why are you not happy? Oh, it's string array, sorry. All right, and then we'll call driver.mux on input names. So this should figure out that we're going to need 2 bits to do this, and it should say smallest is 0, largest is 3. All right, make sense? All right, so now in order to give us our truth table, we're going to need the binary version of these guys. So we're going to need to convert each of these values into their binary version. So what we can do here is we can say for int I is equal to 0, int I is equal to smallest. I is less than or equal to largest. I plus plus. And we'll do a system.out.println integer.parseInt the string version of I in base 2. Largest. Who's in charge of my spelling in this room? You won't know. Oh, I get it. That's going to go the wrong direction. All right, so I'm going to write a quick converter. So we'll say static string decimal to what's up? Is there? Integer.parseInt has a converter.
I used integer.toBinary string.
Oh, that's what this is going to do.
I know.
Okay. So we could say integer.toBinary string that takes an int as a parameter. So there's my I. So this should give me the numerics. So 0, 1, 1, 0, 1, 1. And we want to pad this out to how many bits? Num selector bits. All right. So is there a string.format? Format? What do you take a %2 or % num selectors?
Yeah.
So string.format, my string is going to be percent point, well, it was not necessarily %2.
Percent, like close to the quote. Plus.
Oh, right. You're building a string here,
Yeah.
plus num selectors,
Yeah.
because that's the number of bits. So this is going to give you, although isn't there a point here?
No, I didn't.
Are you sure?
No. I mean, yes, I'm sure.
Because format
Yeah.
format gives you, this is like the printf statement in
Just trust us.
Yeah,
And then you can complain later if it's wrong.
okay.
Yeah,
So what do you want me to say here?
Keep going. So then plus.
Plus s?
Yeah.
Like that guy?
Yep.
Yeah.
And then your argument is the integer.
Yeah. I.
No, the integer that to binary string.
Oh, the thing I have copied.
Yes.
And then
So it's the string.
dot replace after the I.
We say dot replace here?
Yeah.
What am I replacing?
A space with a 0.
Why is there spaces?
That's where you're having it.
So this creates, so this syntax right here creates a string of a certain length, a guaranteed string of a certain length with length num selectors. Or this is just what you found on Google.
Yes and no.
I think that's what this is doing. This is because %s says placeholder for string. So if I was trying to round something, well, not actually round, if I wanted to truncate a number to 2 decimal places, I would say percent 0.2, like f, that would do a float to 2 decimal places. So to me, this reads as a string of size that, because S stands for string. What string am I passing it? I'm passing it this string right here, and what it'll do is it'll force that string to be this many characters long, with characters turning into spaces, and then this will replace those, anything that's a space, with zeros, correct? So, no, we're gonna write it a different way. I mean, this will work. This is a weird format string thing, and it's going to be, when you read through this, if somebody else is reading your code, that code looks funky. So if you want me to finish it here, that's fine. So I'll say replace, and what are we replacing? We're replacing a space with a 0. I don't have my spaces with zeros there. I replace space with 0.
You gotta put single quotes, I think, on the end there.
Single quotes on what?
On the space. Put single quotes.
On this?
Yeah.
And then replace that with a 0. Replacing a char with a char.
Yeah. You're really on the dots there.
Whatever. Static, string pad, string s, int bits. We'll actually take in a bin. Extra zeros will be equal to bits minus bin dot length. So if I want it to be 3 bits and it currently only has 1 element in it, I'll have 3 minus 1, which is 2. So I'll say for int I is equal to 0, I is less than extra zeros, I plus plus, and we'll say bin is equal to a 0 concatenated with bin, ultimately return bin, and then down here we will print out driver.pad, this binary number to this many bits. there's our, do you see how this reads like a human being can read it? The format thing I'm sure would work. It's just a weird way that would be very difficult for somebody who isn't familiar with the specific Java's format, placeholder symbols, and padding stuff to follow. All right, so I'm passing this guy a binary string and a number of bits I want to represent it, and he will spit out that. So if I change my number of bits, if I just double this for no good reason, now I'll have 3 bits, and I'll get more values here. Okay, and if we want our truth table to look extra cool, we really need to have our values spread out, let's say. Because we don't want to just have 0, 0, 0. We want to put extra spaces in there between them, so it looks like our truth table. All right, so I'll go ahead and say static string, I don't know, spread out. This guy will take in a string bin as a parameter. String answer is equal to the empty string. Point I is equal to 0. I is less than bin.length, I plus plus. And we'll say answer is equal to, or answer plus equals bin.char at I concatenated with a space. Then we'll return answer.trim, because there'll be one extra space there on the end. So this guy's just going to go through every character in my string. For each one, it's going to keep the character and then throw a little space after it. And then in the end, I'll trim off that final extra space at the very end of the thing, giving me my 3 characters spread apart. If you want to see what that looks like, it's called spread out. So we'll print out driver dot spread out this guy. And now we have our things looking horrible. Then, hold on. Let's make this a little bit more readable. String bin is equal to the binary string, like that. Then we'll say bin is equal to pad bin by num selectors. Then we'll say bin is equal to driver dot spread out bin. And then we'll ultimately print out bin. An extra parenthesis there. All right, so our spread out takes in a binary number, create the empty string, 0 to bin.length, bin.char at I, concatenate with that.
Can you go back up to mux again?
It's down. It's right there.
Down, sorry.
So bin looks like that. So we'll pass 0, 0 into spread out. Start the empty string. I equals 0. I is less than 2 in this example. I plus plus. Answer is equal to, oh, yeah, so you need to, I think I actually said it out loud. Didn't I say answer plus equals? And then I just didn't put the plus sign in there? So there's my spaces on those guys. That 0, 3 thing is from, where am I printing that? This guy right here. So there's the first part of our truth table. All right. So now what we're going to do, now keep in mind, we might have more entries here than we have things in our array, right? So if I have 3 bits, I can uniquely represent 8 things, but I might have only given you 6 things, which means 2 of these mappings don't go anywhere. I didn't have enough inputs for those. Does that make sense? So they wouldn't be part of the truth table. So I'm going to be going through these guys only so far as I have inputs. So what Mux does is to figure out how many bits am I going to need to uniquely represent my inputs. So I get that for num selectors. Now what I'm doing is I start at smallest and I'm going to largest right now. But I actually don't need to go to largest. I need to go to input names dot length in this language. Okay. It's size in C#. Unless you use array lists, it's size on here. So input names dot length. So this guy will now give me.
That's wrong. You should have 0. Okay.
So this.
More thing wrong.
No.
The console is wrong.
0. This is less than or equal to there. There we go.
And another thing, you should also display the input name.
I'm not done yet.
Okay.
Yeah, we're only getting the right number of bits because right now, if I give you some extra stuff here, so let me just give you 3 extras. Now we're at 7 instead of 8. Right? So we have this possibility of having, this guy's going to say you need 3 bits to represent this. 3 bits lets us represent 8 unique states. But we actually only have 7 inputs. All right, so we're going to be missing the final value here. So this is 1, 2, 3, 4, 5, 6, 7. We don't have the 8th one because we don't need the 8th one. Make sense? All right. And then finally, we're going to have next to each one of these our value.
Why don't we need the 8th one?
Well, if I have, so in this case, I have 4 inputs and you can represent exactly 4 unique values with 2 bits. But if I had 3 bits, I can represent up to 8 unique inputs. But what if I only had 7?
Oh, okay.
If I only actually had 7 inputs, I don't need to represent 8.
So only have 7 inputs at the top right now.
We would only have 7 inputs, which means that we would only have 7 numbers here, even though we would have 1 additional number we could represent with 3 bits.
I didn't realize we only had 7 at the top right now. So that's right.
All right, so right now we're printing out just that binary number. What we want to do is concatenate onto that. Here we can, if we want to make it look super fancy schmancy, we'll put the little dash there. And then concatenate onto input names at bucket I. And that's our, these should probably be a little bit more unique. Your input name should be unique. So if I want to say 3, 4, 5.
I think, yeah, you don't have to be.
Hey, 6. All right, so we have 0, 1, 2, 3, 4, 5, 6. Yeah. So this guy is only going to uniquely represent those particular guys, 0 through 6, which is 7, even though you notice here we don't actually have a 1, 1, 1. We didn't need that extra representation. But if I change my inputs here and I go ahead and give myself another one of these, now I'll have the 1, 1, 1 for representing that next guy. But if I give myself another one of these, now I just trickled in to needing 4 bits. So now I have 4 bits, even though I've barely used that 4th bit at all. Make sense? All right. So is this a truth table generator for multiplexers?
Yep.
I think this accomplishes what we were trying to accomplish.
Yes, exactly.
Questions on this one? So do we understand the relationship? So what was the goal of this question? What was it trying to help us understand? Trying to understand the relationship between, first of all, what does a multiplexer do? What's the job? If I have this tool, I go into Home Depot and I pull a multiplexer off the shelf. What does that tool do? Why did I buy that guy? Go ahead.
Take 4 inputs and only spit out 1, I guess.
Okay, so take some number of inputs
Yeah.
and spit out and select between one of them, right?
Yeah.
So take some number of inputs and spit out one output based on my selectors here. All right. So it's kind of like over here we have like an HDMI switch box thingy, right? Where we have a bunch of inputs coming into it, and maybe we want to have 4 different inputs that go to the single monitor, and depending on which little switch state, which selector we've plugged in, it shows a different picture on this for which of the 4 sources, or 5 sources, or 6 sources, or 10 sources, whatever it is. But we're going to need more switches in order for that to work. So inside of that HDMI, that's what it's like a reverse HDMI switcher, I guess. It would be an HDMI multiplexer. There is a multiplexer that has switches like this that would determine which signal gets through and which ones do not. Make sense? Go ahead.
What's a large scale example of this?
What's I guess a large scale example. Well, you mean besides the HDMI thing?
Yeah, besides this house, like it's just an
In
example.
CPU, we have so many multiplexers.
Well, yeah, but I mean, you're looking for something like bigger, more obvious, right? Than like something intricate inside of a CPU.
No, I'm just thinking like, is there another situation where like maybe you have a whole lab of computers and you only want one of them to display something or something along those lines?
Well, that's specific from a displaying perspective. I mean, this is really about we have some number of input signals and we only want one of them to get through and all the other ones are blocked. So, I mean, you could think of it like a soda machine. Yeah, where you push the button and depending, you have 10 different syrup things coming in. And when you push the button, depending on which thing you do, that sets the state of the switch and the right kind of soda comes out. That would be a multiplexer as well. I mean, there's just plenty of examples, and this is, if we kind of come down to, let's show it in the CPU. Processor design. Well, they don't give us you have to pull apart one of these pieces to get to the multiplexer. We saw it with our registers.
Yeah, I think the Cortex decider has a little faster.
I don't see anything.
No, there isn't one here.
They have a little small one. Right?
Where?
And what's not one?
Up, over, left, right?
I don't know what's right. The left, top, left. Right. That is yeah. So that line.
Oh, this guy right here.
Yeah.
Yeah, that's only a single bit switch, so I guess that's true. Okay, well, so that actually comes back to a question that you and Jordan were asking last night. So, this is similar to it. So this is a write switch, and we're deciding whether or not we can write based on, we have 2 different signals coming in here, and only one of them gets through based on the value of this switch. Where does the value of this switch come from? It comes from one of the inputs on my control. So if I follow this wire down, it's this guy right here, which will represent one of the pins coming into my CPU.
Okay.
Huh?
How can you even see that one?
This one? Because I have ninja eyes.
I really thought that is a buffer at the beginning.
Yeah. Yeah, so this is our controller. So we can think about these as being our pins coming in from our CPU. It's an oversimplification, but let's just say that's the case. So one of these pins, this guy right here, determines what the value of this switch coming into this is. And that either lets the 0 through or the 1 through. And that becomes the input into this register file. But I mean, I really think, so this gets technical, right? This is the scary CPU stuff. I really think the HDMI switch is a really clean example. You know, we have a DVD player, a computer, a PlayStation, and I don't know, let's just say there's those three. We're still going to need 2 bits to represent the 3. We won't use all 3. Right, so we have 3 different HDMI cables plugged into this. One for the PlayStation, one for the PC, one for the, what was the other thing I said? Blu-ray player. And depending on my switch, one of those 3 devices shows up on the one screen. So I have one HDMI cable plugged into the back of this guy, one output. And depending on my state of my switch, is it 0, 0 or is it 0, 1? So maybe 0, 0 is the PlayStation. 0, 1 is the Blu-ray player. 1, 0 is the, what do I have, a PC? What else do I have? Whatever. Yeah, so whatever. So it's those. And then I'm not even using the 1, 1 in that case. So there was the 4-to-1 HDMI switch, but I only actually plugged 3 devices into it. So I only had 3 inputs. So when I hit that little switch on it, it's flipping those bits to the right thing to select the kind of guy.
So
Yeah.
we have one here, right?
Yeah, there's some HDMI switcher box thing over here somewhere.
We have 2 inputs. One is the laptop. Another one is there is a button desktop. So the switch controls which input display
Yeah.
here.
Is this, I feel like this is a dumb question, but is this like the same thing that you have like on a TV when you set like which HDMI you want to use?
Whether it's implemented that way inside, we don't know, but it certainly could be. Yeah, when you select HDMI 0, it's going to, that selector is going to be what comes out of the, it actually would probably be a decoder. It'd be a decoder because what you have is you have multiple inputs coming in. Well, no, you can think about it as a multiplexer as long as you treat your screen as the output. Yeah, that's correct.
Is that a screen and output?
It would be, yeah, but we're kind of being. The screen is the output if our eyes are the input. It's a little bit of a weird example, but I think you're right. So if we say whatever shows up on the screen is based off of which input you selected, HDMI 0, 1, 2, 3, and you have 4 devices plugged into the back of your TV, switch 0, 0 might be HDMI 0. Switch 0, 1 might be HDMI 1. 1, 0, HDMI 2. 1, 1 is HDMI 3. That can be handled with a multiplexer.
Could you technically say, like, it's a multiplexer talking to another multiplexer? Because, like, if you're so if you're plugging in, or if you're specifically saying, okay, HDMI 1 is going to then tell that, like, use HDMI 1, which will then tell the TV.
Well, yeah, I mean, potentially, even though we only have one input going to our TV, but yeah, so since our TV is currently set on HDMI 2, I think is what this guy is, then that multiplexer is set up to just always let HDMI 2 flow through to the screen. And then this switch box over here is also a multiplexer that's choosing which of those inputs flows through the single cable going into this, which flows through the one HDMI 2 output that we always just have set. That make sense? So that's I guess a real world problem of what a multiplexer does. It's a switch box. So lets you decide, given some number of inputs, how can you switch between them based on your current desire. And you need some number of bits to accomplish that. And that's what this homework, this question on the homework was about creating. I have so many devices I want to plug into my HDMI switch box. How many switches, how many unique switch states do I need in order to support that? That make sense? All right, so questions on this homework assignment, or this question.
Is it related to anything of the rest of the homework?
The who?
No.
Does it related to anything beneath?
Oh, all the other, anything else in the homework?
Yeah.
I don't know. I haven't looked at the next question. I wrote this days ago. I wrote this a week ago. So let's find out. It's like opening a present.
I think if you think about composite memory, there's some similarity
We're
there.
not saying.
All right. Well, we'll quite possibly. Quite possibly.
If you go back to the code again, box the print statement, you gotta do something really fast. I didn't catch it. Okay. We're good.
All right. So next question is, why is this so small?
Yeah, you're telling me.
You can open it, click the link.
Well, click this.
Yeah.
I think it has to do with the resolution of the TV. I have that same problem out.
Well, no, it's small on my computer too. Ninja. Cancel. Well, all right, this made it way worse. Hold on, we're just going back. I'm going to use my X-ray vision. We're going to do this. All right. A class called memory, whose constructor takes in the number of cells and the bit width. Okay, so let's create our class called memory here.
Of what?
Who? Bit width. Bit width. The number of bits. Number of bits wide. Yeah, bit width.
That's not what you said.
A class called memory whose constructor takes in the number of cells and the bit width.
Oh, that's not what I read.
What did you read? What do you think that meant?
What that is?
Huh?
What that is?
So you translated bandwidth into how many bits it is? I'm not sure how bad that is. So you read it wrong but translated it correctly. That's like somebody saying jump but you sit down.
But you jump.
But you jump. All right. So I knew tonight was going to be an
This is
interesting
not a
class.
literature class.
Okay, so we're doing a new class called memory. How are we doing on time? All right, we could do at least memory. Does this question take less than 18 minutes? Memory.
I think memory is
We're going to find out. All right. This guy takes a constructor. It takes in a number of cells and the bit width. So, for instance, 4096 and 8. So, number of cells would be 4096, and 8 is the number of bits per cell, would give you 4,096 buckets, each capable of holding 8 bits. Okay? So 2 and 3 are going to share some stuff here, right? Question 2 and question 3, they're going to share kind of these, what a cell is. So a cell is going to be kind of a number of bits. So I'm going to create a couple of other things here. So I'm going to come in here and I'm going to say new class.
bucket.
And we're going to call this guy a cell.
Okay. You are not using buckets.
Well, the language in the book is cell, right? Number of cells. The book uses cells, doesn't it?
You are using buckets. In your
Correct.
previous-
Yeah. But I just want to use the words the book uses. The book uses the word cell for memory.
Does it matter?
Well, I don't know. Might as well match up to the book if I'm trying to get you to understand the book better.
Let's go and check what it said.
Well, this is not the part. Was it? Ninja? Composing memory.
I think this exercise is 6.1.
6.1?
Yeah.
This guy. So, memory is a digital component, retains bit values consisting of n words of m bits. Each word has a unique address, blah, blah, blah. All right, so it calls these guys words. All right,
Nice.
delete.
We determine the terminology.
All right, so we're deleting cell.
rename?
Well, I can. Fine. I'll go into cell. I'm going to say refactor, rename. We'll call this word. Aha! Oh, so refactor doesn't actually change the name of the file?
You are looking at memory.
Aha! All right. So this guy is going to keep track of a string. Do we want to do it as a string? Or do we want to do it as an array? I'm going to write stuff here.
Array, the problem is, okay, it's fine.
I like strings too, you're right.
It's a fact.
So we're going to say we're going to have a private string called bits. And we're going to have private string or private int bit width. So we'll create a public constructor. This guy will take in a bit width. And when a word is first born, we can just go ahead and fill it with that many bits of 0. We don't need to give it an initial value. Take an int.
Where will you hold the address?
Well, the address is not part of the word. A word is a word. The address is going to, memory is going to have an address. Bucket 0 will have a word. Bucket 1 will have a word. Bucket 2 will have a word. So 0, 1, 2, these are the addresses of our, so addresses are just indexes of our array of words.
And you also need the read enable and write enable here.
Not right now. Right now we're writing a constructor.
Okay.
Yeah. One little tiny step forward, right? One little tiny step forward. Can't conceive of the entire problem at once, otherwise we'll never get anything done. So we're having a constructor for word. Word is going to fill up, well, it's going to set bit width. So this dot bit width is equal to bit width. Blah, blah, blah. This dot bit width is equal to bit width. And then we'll go ahead and say for int I is equal to 0, I is less than bit width, I plus plus. Right before that, we'll say this dot bits is equal to the empty string, and we'll say this dot bits plus equals 0. Actually, putting a 0 on there would have just worked fine, but. So we'll fill it up with a bunch of zeros. All right, so if my bit width was 8, I'll get a string with 8 zeros in it, and and then bit width gets set to 8. If bit width was 16, which might be what we do when we look at, because we're doing horizontal memory first. When we look at parallel memory, bit width might be 16, so we can store larger things but fewer of them. Okay, so we'll be able to use Word for both of these guys. All right. So that's what Word is able to do right now. We can build words, but can't do anything with them yet. We'll add some additional ability here in a few minutes. All right, so we'll go ahead and open up memory. We have our constructor for memory. And this guy says that for memory, we should take in a public constructor that takes in a couple of pieces of information, takes in a number of cells, so that's our number of words, and a bit width for each of them. All right. And so we're going to have a private word array. We'll call this the words. And this guy is going to have a public constructor, so public memory. And this will take in a int num mem cells. That become num words. And then an int bit width. And it's going to go ahead and say this dot the words is equal to a new word array of size num words. And then we'll say for int I is equal to 0, I is less than this dot the words dot length I plus plus this dot the words at bucket I is equal to a new word of size bit width. So that'll fill my memory up with stuff.
I have a small question related to Java.
Yep.
When you have in the private words array, why the declaration doesn't require the size?
Why doesn't it require it?
Uh-huh.
Well, can't I say int a like that?
But the A will know it has the size of the memory.
Well, that's not an error either. A does not require a value. The definition, so the syntax for variables is type followed by var name, the formal language for this, and then optionally equals value, semicolon. This is the language syntax for defining a variable in C-based languages. We have the variable type, we have the name of the value, or the name of the variable. Optionally, we can give it a value. We can define a variable but not put a value in there if we want. That's always allowed.
So my
You shouldn't use it before you put a value in there, but
my question is this: say, for instance, if you have integer, and when you're declaring it, we already given a memory address to this variable, right?
yes, because of how primitive types work. You're right. We do give and we give a memory address for this guy too. The variable called the words has a memory address.
Okay.
He doesn't contain a memory address that points to an actual word until we fill it.
I see.
Yeah.
Because it's not primitive.
Yeah, all variables, well, no, not even that. All variables, regardless of whether it's a primitive or an object, any variable will have a memory address. We have to store that variable association somewhere. But, so if I have int a here, like that, a will have a memory address somewhere. But a primitive type says at that memory address, store the value. An object type here, so the words is going to have a memory address where that variable lives, but the value that lives at that memory address will be a pointer to an actual word someplace else.
Doesn't really need to have a value, a memory of the value.
Yep.
The reference is initiated, but
the reference is the value.
Value doesn't.
All variables have a name, and that name is going to be associated with some memory address. And then a variable also has a value. Some values might be primitive types like an int. Some values might be pointer types like words are going to be, where we point to an actual constructed word somewhere else in memory that has a new memory address. So it's like that's what we say. This variable holds a memory address which points someplace else. All right, so here is our memory. And then if we want to go ahead and quickly say public void display, just to test this guy, we'll say for word w in this dot the words. Let's do some stuff and let's teach a word how to display itself. So I'll go into word and we'll say public void display, and this guy will say system.out.println this dot bits. And then for each word, we'll say w.display. All right, so now we can create memory. I'll just comment out these two things here. And I'll go ahead and I'm going to say I want memory. And memory takes in a number of cells. So just to keep this simple, I'm going to say 100. Actually, let's say 10. Right? And then a bit width. So we'll say 8. And then we'll say m.display. So we'll get 10 8-bit numbers, which represent memory locations. That's what we're going to use for our horizontal. But if I choose to have more, so just to kind of give you the idea here. So for horizontal, we might have 10 different individual buckets for storing 8 bits, which we just saw. Or I could have 5 different locations, each capable of storing 16 bits. the total number of bits I'm storing is the same. The difference is, am I storing less bigger things or am I storing more smaller things? That's the difference between whether or not we organize our memory chips in composite memory as whether we organize them horizontally or we organize them vertically. Do we want to store more smaller things or do we want to store less bigger things? That makes sense? All right, so we now have the ability to do our memory. Our example here was, the 4096 by 8, but, you see that is a lot of memory that gets printed out, just walls and walls and walls of stuff, so maybe a little difficult to debug at that level. So for right now, we'll just keep it at a 10. All right. Okay. Your class, or you class should support 3 functions. Write, which attempts to write data to memory. Read, which attempts to read data from memory. And set state, which delivers an address. Okay, ren is read enabled, and when is write enabled. All right, so just before we take a break here, let's just go and review memory here. All right, so we have something that looks like this. And what's this guy going to do? In our picture, we have an array of words. That's what this guy is, right? This is an array of 8-bit words. So our bit width is 8. All right, and we have 4096. So if to build that exact thing, I think that's what I currently have in there. Oh, no, I had changed it. That builds that exact model. 4096 by 8. All right. Now we have several different things memory can do. So memory we can write to or we can read from. Makes sense, right? Memory is like a little bucket. So I can put a little bucket here. But I'm only allowed to do one thing at a time. I can either put something into the bucket or I can read from the bucket. I kind of get a copy of it. I don't actually remove it from the bucket. It's whatever. So I can write to it or I can read from it. Now, the book says that reading is more powerful than writing. Okay? So if I try to write and read at the same time, read wins. Okay, read is a stronger signal. So, so the way this works is we can present data to the right. We can try to read from the read, but not until we set the right flags. Does this trap door open, letting whatever data was waiting there fall in? Okay, in order for this data up here to fall in, we have to, well, first of all, you have to have an address. So this address says, which of my buckets will this guy fall into if I were to allow it to write? That make sense? It's an important distinction because I can write to W data here. That does not get it into memory yet. In order to actually get it into memory, I need to tell it where do I want it to go, and I need to allow it to go. And to allow it to go, I need to set when to 1, and I need to make sure that ren is 0. That's the only way a write can happen. If ren is 1, it doesn't matter what you set when to, it will not write. All right, because a read is more powerful than a write is. So as long as ren is to 1, this memory is open for business to read from it. Nothing can get written to something that's currently being read from. It kind of makes sense why that works that way, doesn't it? You don't want to, if something in your computer is reading from memory and is in the middle of doing it, you don't want something to overwrite what you're currently reading from. So that's kind of it makes sense why it protects it that way. As soon as we shut down our read, as soon as we said, yeah, okay, I got what I needed, then we would set the read back to 0. Presumably, right? This is kind of like the idea, you go to the sink, you start filling the container up with water, because you turn the faucet on, you set ren to 1. Start filling the container up with water. And then when you're done, what do? Well, most of us, human beings, turn the water off, right? We set Ren back to 0 and then leave with our data. Okay? Some of us just leave, still reading. Nobody's reading from it, but it's still pouring out of there. No harm, no foul. All right? But as long as we left that faucet on, let's say we're like back to our soda machine example. So I walk up to the soda machine, I get my Diet Mountain Dew. So I push the button, I got Diet Mountain Dew coming out. And then I'm kind of one of those jerks. I duct tape the button open, right? Now at that point, Mountain Dew's still flowing out. Somebody behind the scenes can't change that to something I actually probably could, but let's just assume in our memory example they can't. They can't change out the Mountain Dew to be Pepsi, okay, because somebody is currently reading from the Mountain Dew spigot. And you can't write to that place if somebody's currently reading from it. All right? So we can present information we intend to write here, but it does not actually get written until we have a place to write it and we flagged when as being a 1, we should write, and Ren is set to 0. We're not reading. Okay? So we're going to be setting the state of this so that we're prepared to write data when and if we actually allow ourselves to write data. Similarly, when somebody reads data, we will read whatever data is stored at this particular address whenever Ren is set to 1. Does not matter what when is set to. If when is 1 and Ren is 1, we're reading all day long. Reading is more powerful. So we do not have to turn the write off in order to read, but we do need to turn the read off in order to write. All right, make sense? Mm-hmm. All right, so let's take a 15-second break. All right, let's take 10 minutes. We'll come back at 1, or I'm sorry, not 1:12. That's adding to my hour. We'll come back at 7:18. Right? No, 7:16. 7:16.